What's going on, guys? We are going to do a little bit of a review of some pre-calculus and introductory calculus concepts. So the text that we're going to be using to kind of guide this is Calculus Volume 1 by Herman and Strang. I'm a big fan of it, especially as we dive into it and look at some of the questions. I think that they touch on a lot of really deep ideas. So let's get started. Let me just share my screen with you. Let's see. So the first thing that we're going to do is kind of build up the connection that we have with considering some secant lines and how they can sort of converge to tangent lines. Visually, as has been discussed in the past, the idea is that if I have some given function and I want to find the rate of change at a specific point, I'm looking for the slope of the tangent line. A really good way of approximating this is by picking a second point, and as we continue to cause the difference in the x values to become arbitrarily smaller, we're just going to get a better and better approximation of the actual tangent line until we have nearly a perfect match. And this is really the foundation of calculus, that as we introduce some infinitesimal values, we will approach a very valid convergent value. Okay, so let's look at what this question's asking. So we are saying that we have some points p1, 2, and q, x, y that are on the graph of the function f of x equals x squared plus 1. So we want to complete the following table with the appropriate values, the y-coordinate of q, the point q, x, y, and the slope of the secant line passing through points p and q. We're going to round to 8 significant digits. All right, so let's just start to list these through. So 1a. So the x value we're being given is 1.1. So the y value is just going to be plugging 1.1 into the function. So let's just go ahead and enter that into our calculators. I'm just going to type in the function, and then I'll just look it up on a case-by-case basis. I'll just start writing out all these values here. So A, B, C, D, E, F, G, H, I, J, K, L. Okay, so let's see. I'm going to calculate the value. First, we'll plug in 1.1, and let's see what we get for this. That is going to be 2.21. That is the y value. So the associated coordinate we have here, I'm going to space this out a little bit better. Maybe I'll write the I through k below. This is going to be the point 1.1 comma 2.21. So now for the slope of the secant line, well, that's just going to be the rate of change between the two. So that's just going to give us 2.21 minus 2 over 1.1 minus 1. And this is the process we're going to repeat for I through L. Let's see, 2.21 minus 2 divided by 0.1, that's going to be 2.1. All right, so going down the list, that would be 1.01 plugged into this function. That's going to be 2.0201. So the coordinate we have is 1.01, 2.0201. So now we're just going to find the difference, the slope of the secant line, by taking the difference in the y's divided by the difference in the x's. Okay, so this slope is going to be 2.01. Let's continue forward. So 1.001, if we plug that in, is going to give us 2.002001. So that's the coordinate 1.001, 2.002001. And if we find that change divided by 0.001, that is 2.001 for the slope of the secant line. And we can already see the pattern. It looks like this number is starting to converge towards 2. Well, for the sake of completeness, let's go ahead and verify that. 0.0001 squared plus 1. That is 2.00020001. So that's the coordinate 1.0001, 2.0002, 0001. Alrighty. So now minus 2 divided by 0.0001, that is 2.0001. All right, so that completes all of part 1. Number 2, use the values in the right column of the table to guess the value of the slope of the line tangent to f at x equals 1. So all these x values were approaching the point P. We're essentially getting closer and closer, kind of that limiting process I showed graphically previously. So we can infer here that the slope of the tangent line is likely going to be 2 based on these results. For number 3, use the value in the preceding exercise to find the equation of the tangent line at point P. Graph f of x and the tangent line. So I'm going to choose to write this in point slope form. The point that this tangent line will definitely go through is the point 1, 2. So our line would be y minus 2, the y coordinate is 2, is equal to 2 times x minus 1. In other words, if I redistribute this, maybe we want to get it into point slope intercept form rather. This is point slope form. We want it in slope intercept form. I'll distribute out the 2. So that would be y minus 2 equals 2x minus 2. Add 2, so that would be y equals 2x. And then we'll just draw a graph. So x squared plus 1 is just a parabola that's been shifted up 1. So we'll just zoom in here a little bit. So that would be up 1, 3, 1, up 3. So our parabola is going to look something like that. And then the line y equals 2x. That's going to start at the origin, go through here, 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 and here. So that's going to look something like that. We can even see visually that it looks like we've done everything correctly. This certainly looks like it would be a tangent line at this point. All right. Let's see. Is there anything else that we had to do? The next part is actually referring to the next exercise. We don't need this. So we have completed this problem. We found what these values are converging towards, the slopes of the secant line, and in that sense, they are converging towards the slope of the tangent line. We then inferred what the tangent slope was, completed our graph, drew it out, and we can see that this seems to be logically consistent with exactly what we would expect. And when we get further into some calculus, we'll see that indeed the derivative of x squared plus 1 is 2x. So we definitely approached this correctly. Let's look at this next one. So for the following exercises, consider a stone tossed into the air from ground level with an initial velocity of 15 meters per second. Its height in meters at time t seconds is h of t equals 15t minus 4.9 t squared. Compute the average velocity of the stone over the given time intervals. So for this, over this interval, the average velocity is the slope of the secant line. It's just asking, on average, what is my, well, without repeating it too many times, what is my average rate of change? So I'll do part A. The rest of them would follow very, I'll do all of them. They'll all follow very similarly. The first thing I'll do to expedite this is I will just enter this function into my calculator so that we can just call on these specific values. So minus 4.9x squared. I'm going to graph that, just let it complete its thing. So when we plug in 1, we have the point 1, 10.1. And I'm just going to follow through for all of these points we're given. 1.05, just so we can expedite this. 1.05, that's 10.34775. 1.01, that would be 10.15151. Let's see, 1.005. That would be 10.125878. And then finally, let's see, 1.001. 0.001, that would be 10.105195. All right, so now to find the average velocity, we're just going to take the change in y over the change in x, because this would be the slope. For this one, we would just be using these two coordinates here. So I'm just going to calculate that difference. That would be, let's see, 7.5 minus 0.1 divided by 0.05. That's going to be 4.955 meters per second. That's the average velocity. Let's see. Then from there, for 1.01 to 1, that would be 0.15151 minus 0.1 divided by 0.01. That is going to be 5.151 meters per second. This is going to be, now we're using, let me erase these. Now we're using these two, so 0.125878 minus 0.1 divided by 0.005. That is going to be 5.1756. And now here, we are just going to be using these 2 points. So that's going to be 0.105195 minus 0.1 divided by 0.001. And that is going to be 5.195. And these are all meters per second. All right, so now use the preceding exercise to guess the instantaneous velocity of the stone at t equals 1 second. So, well, okay, based on this assumption, it seems like we're slowly getting closer to, I would guess, 5.2. So at the moment where t equals 1, so at t equals 1, we would guess that the instantaneous velocity is going to be approximately 5.2 meters per second. And when we get a little bit further into our study of calculus, we'll be able to see that the answer is truly 5.2. And as we get deeper, like I said, learning a little bit more about what's going on here, we'll see how we can arrive at that answer. Great. Okay, so now I cut off what the question's asking here, but basically we're being asked to fill in this table of values and try to guess the limit. Then we're gonna verify it graphically and determine whether or not our guess was correct. And if it was incorrect, we should try to surmise why that might be, why a table of values might present some inaccuracies. So let's start with this first function. So this first function is sine of pi over theta. So we can go ahead, and again, just to expedite this, I am just going to graph it on my graphing calculator, and then we'll plot it in Desmos so you can see visually what exactly is happening here, and we can look together at why this might be a problem. So, okay, plugging in negative 0.1. Let's just go in order. So negative 0.1, we get a y value of 0. So let's see, negative 0.01 tells us again 0. Maybe it's some infinitesimally small decimal and the calculator is just rounding it to 0. But who knows? Let's see. So plugging in negative 0.01, you get 0. Plugging in negative 0.0001, we get 0. We'd actually end up getting 0 for every single one of these values. So now let's go ahead and plot this function, because we can infer that the limit as theta approaches 0 of sine of pi divided by theta should be 0. Let's plot this and see what we end up getting. So we'll just go to Desmos over here. And we're plotting the function y equals, let's see, don't want to do that. There we go. Y equals, where's my sine function? Sine of, I want pi divided by x. Oh man, all right. So we see some like really heavy oscillations. Let's kind of zoom way in and see if we can reach anything valid. It seems like this is a kind of a heavy load for Desmos to take on, but we can see that it just looks like it's like all crowding around zero. Let me just zoom out a little bit so we can look at that again. If I zoom way out, I think this is a little bit clearer to see what's happening. If we zoom way in, we have all these crazy oscillations. But zooming out, it does look like it's just sort of like bouncing around zero, like it's kind of coming in from both sides and then just hits zero. So a valid question is, why is that the case? Well, that's the case because whenever we introduce any of these values, these are all just multiples of pi. So for values close to zero, we are really just evaluating, in this case for negative 0.1, that would be sine of negative 10 pi. Negative 0.01 is sine of negative 100 pi. Positive 0.001 is sine of 1,000 pi. And we know that multiples of pi going around the unit circle all give us zero. So the limit here is zero. The graph does confirm that, even if it's a little tricky to make sense of, given how insanely it oscillates. But that does line up with our intuition. Now let's see what happens in this second case. So we want the limit as alpha approaches zero from the right of 1 over alpha cosine of pi over alpha. So let's see, let's plug this into our calculator. So cosine of pi divided by x divided by x. And we'll just go ahead and let that do its thing. And then we'll plug in some of these values and see what we got. So let's see, plugging in 0.1, we get 10. Plugging in 0.01, we get 100. Plugging in 0.001, we get 1,000. All right, well, I'm going to guess the next one's 10,000, but let's confirm that, 0.0001. It is indeed 10,000. So, okay, well, it looks like we can infer that the limit as alpha approaches zero from the right of this function, it looks like it's just heading off towards positive infinity. Let's see if that is a valid conclusion. So plotting this, we have y equals, go back to my functions, cosine of pi divided by x, all divided by x. Oh man, all right, this is really bouncing around. Let's see if we can make some sort of sense of this. So I only want to see what's happening on the right. I'm going to zoom out of that a little bit. We can see it's kind of forming this sort of like envelope shape. And it looks like if we were to trace it out from the right, it is bouncing up. It is going up and up and up. So the only problem we also have is it looks like that we have this sort of symmetry coming down as well. Again, we're just looking on the right side of the graph. So it looks like it's just wildly oscillating even just on the right side. The actual limit appears to be that it doesn't exist. And the reason why is that even when x is restricted to positive values as we go off to zero, cosine is an oscillating function. So cosine is going to continue bouncing between 1 and -1. Like hypothetically, we just kept plugging in values that got closer and closer to zero. So we had, values like cosine of 10 pi, cosine of 100 pi. Those all happen to be even values. But if I were to choose something that would give us an output of like cosine of 9 pi, that would be if I chose x equals 1/9. Well, cosine of 9 pi is -1. So that would be going down to -9. And then as we get closer and closer, it's going to shoot up to, positive 10, -11, positive 12, -13, positive 1 million, -1 million and 1. It's just going to keep bouncing like that. So the actual answer is that this does not exist. And this is simply just a shortcoming in terms of tables of the values we chose. So we didn't do anything wrong. The values we chose indicate it might be positive infinity, but that's not actually the case. And that's something good to watch out for with trig functions. Remember, sine and cosine naturally oscillate. They bounce between positive and negative values. The limit itself of a trig function tends to not exist. If we took like cosine of x and let x go to positive infinity, that limit wouldn't exist. For wildly large angles, it's not going to converge to any particular value, and we get the same outcome here. Okay, so now looking at this final example, here we're given a graph to interpret, and we want to verify whether these statements below are true or false. So they're claiming the limit as x approaches 10 of f of x, presumably this is f of x, equals 0. Let's see, a limit exists, the limit as x approaches a of f of x exists if and only if the left-sided limit is equal to the right-sided limit where both exist. This is the definition that we're going to be using. So let's see if that seems to hold. Well, if I come in from the left as x approaches 10, I am coming towards 0, it seems. Coming in from the right, I'm heading towards 0, so this seems true. Let's see, 47, the limit as x approaches -2 from the right of f of x equals 3. -2 from the right. Well, let's see, this is kind of shooting up here from the right. It looks like it's even either heading towards 7, maybe positive infinity. Who knows? I mean, the fact that they didn't specify a point at 7 tells me they're implying it's going to positive infinity. This statement is false. From the left, it's coming to -2. It's actually defined at -2, but from the right, this is not the case. So this is false. 48, the limit as x approaches -8 of f of x equals f of -8. This is referring to the definition of continuity. So we're going to have continuity if the limit as x approaches a of f of x is just that limit. That means, hey, everything I'm approaching from the left and right, I'm just plugging in that point. Let's see if that's true. So -8, well, let's see. The limit coming in from the left looks to be about -6. The right is -6. F of -8, though, is defined to be this value up here, which looks like it's about -3. So this is not true. We have a removable discontinuity here, and in that case, it's discontinuous. So this is not true. The limit as x approaches 6 of f of x equals 5. Let's see, going towards 6. Well, let's see, from the left, it's heading towards 2. From the right, it is heading towards 5, but the left and right-sided limits don't match up. So this limit actually does not exist. F of 6 is 5. It is defined there, but the limit is not equal here. And that makes sense because we have a jump discontinuity. This is discontinuous, so we wouldn't expect the definition of continuity to hold. This video ended up being a little bit longer than I was hoping, but I really wanted to dig into some of these concepts in order to show what exactly a reasonable thought process would be. So when going through problems like this, you definitely want to think less about how can I apply a formula? How can I plug in a function and just get an answer? And think about the reasoning that's underlying it. That's going to be an exercise we'll practice a lot as we dive deeper into pre-calc, further into calculus, really any math subject you take. I find that it becomes much easier when we kind of break down this barrier of always trying to just plug and chug and reasoning everything out instead. I hope you found this video useful. If you have any questions, comments, concerns, do not hesitate to reach out and contact me. I will see you soon.